Chapter 6 Ionic and Molecular Compounds. In nature, atoms of almost all the elements of the periodic table are found in combination with other atoms. Only the atoms of the noble gases, helium, neon, argon, krypton, xenon, and radon, do not combine in nature with other atoms. A compound is composed of two or more elements with a definite composition. Compounds may be ionic or molecular. In an ionic compound, one or more electrons are transferred from metals to nonmetals, which form positive and negative ions. The attraction between these ions is called an ionic bond. We utilize ionic compounds every day, including salt and baking soda, milk of magnesia, or calcium carbonate, and may be taken to settle an upset stomach. In a mineral supplement, iron may be present as iron 2 sulfate, iodine as potassium iodide, and manganese as manganese 2 sulfate. Some sunscreens contain zinc oxide and tin 2 fluoride. Toothpaste provides fluoride to help prevent tooth decay. Precious and semi-precious gemstones are examples of ionic compounds called minerals that are cut and polished to make jewelry. For example, sapphires and rubies are made of aluminum oxide. Impurities of chromium make rubies red, and iron and titanium make sapphires blue. A molecular compound consists of two or more nonmetals that share one or more valence electrons. The resulting molecules are held together by covalent bonds. There are many more molecules than there are ionic ones. For example, a molecule of water, H2O, consists of two atoms of hydrogen and one atom of oxygen. When you have iced tea, perhaps you add molecules of table sugar, C2H22O11. Molecular compounds consisting of mostly carbon and hydrogen are known as organic compounds. Familiar examples include propane and butane and ethyl alcohol. Your food contains bigger organic molecules known as biomolecules, such as a polysaccharide starch, which contain many covalent bonds between atoms of carbon, hydrogen, and oxygen. Section 6.1 Ions, transfer of electrons. Most of the elements, except for the noble gases, are found in nature combined as compounds. The noble gases are so stable that they form compounds only under extreme conditions. One explanation for their stability is that they are filled valence electron energy level. Compounds form when electrons are transferred or shared to give stable electron configurations to the atoms. In the formation of either an ionic bond or a covalent bond, atoms lose, gain, or share valence electrons to acquire an octet of 8 valence electrons. This tendency of atoms to attain a stable electron configuration is known as the Octet Rule, and provides a key to our understanding of the ways in which atoms bond and form compounds. A few elements achieve the stability of helium with 2 valence electrons. However, we do not use the Octet Rule with transition elements. Ionic bonds occur when the valence electrons of atoms in metals are transferred to atoms in nonmetals. For example, sodium atoms lose electrons and chlorine atoms gain electrons to form ionic compound sodium chloride. Covalent bonds form when atoms of nonmetals share valence electrons. In the molecular compound of H2O, water, or C3H8, propane, atoms share electrons. Positive ions, loss of electrons. In ionic bonding, ions which have electrical charges from which atoms lose or gain electrons to form the stable electron configuration. Because the ion energies of metals of groups 1A, 1, 2A, 2, and 3A, 13, are low, metal ions readily lose their valence electrons. In doing so, they form ions with positive charges. For example, when a sodium atom loses its single valence electron, the remaining electrons have a stable electron configuration. By losing an electron, sodium has 10 negatively charged electrons instead of 11. there are still 11 positively charged protons in its nucleus, the atom is no longer neutral. It is now a sodium ion with a positive electrical charge, now called an ionic charge of positive 1. An ionic charge is the charge of protons plus the charge of electrons. So an ionic charge of positive 1 has 11 positive protons, but 10 negative electrons added together gives you positive 1. In the symbol for sodium ion, the ionic charge of positive 1 is written in the upper right-hand corner in a positive where 1 is understood. The sodium ion is smaller than sodium atom because the ion has lost its outermost electron from the third energy level. The positively charged ions in the metal are called cations, and the use of the name of the element. Magnesium in metal in group 2A, group 2, obtains a stable electron in configuration by losing 2 valence electrons to form a magnesium ion with a positive 2 ionic charge, Mg positive 2. The magnesium ion is smaller than the magnesium atom because its outermost electrons in the third energy level were removed. The octet in the magnesium ion is made up of electrons that fill the second energy level. Negative ions, gain of electrons. The ionization energy of a nonmetal atom in groups 5A, 6A, and 7A, 15, 16, 17, is high. Rather than to lose electrons to form ions, a nonmetal atoms gain 1 or more electrons to obtain a stable electron configuration. For example, an atom of chlorine with 7 valence electrons gain 1 electron to form an octet. Because it now has 18 electrons and 17 protons, the chlorine atom is no longer neutral. It becomes a chloride ion with an ionic charge of -1, which is written as Cl negative, but with a 1 understood. The ionic charge is 17 protons minus 18, being electrons. They add up to -1, or summing 18 electrons and 17 positives. A negatively charged ion, called an anion, is named by using the first symbol of its element name followed by "ide." The chloride ion is larger than the chlorine atom because the ion has an additional electron, which completes its outermost energy level. Formulas and names of some common ions. Lithium, Li1, positive. Sodium cation, Ni positive 1. Potassium ion, potassium positive 1. Magnesium ion, magnesium positive 2. Calcium positive 2. Barium ion, barium positive 2. Aluminum ion, aluminum positive 3. Nonmetals, nitride, N negative 3. Phosphide, P negative 3. Oxide, O negative 2. Sulfide, S negative 2. Fluoride, F negative 1. Chloride, Cl negative 1. Bromide, Br negative 1. Iodide, I negative 1. Ionic charges from group numbers. In ionic compounds, representative elements usually lose or gain electrons to give 8 valence electrons, like their nearest noble gas, or 2 for helium. We can use the group numbers in the periodic table to determine the charges for the ions of the representative elements. The elements in group 1 lose 1 electron to form an ions with a positive 1 charge. The atoms of elements of group 2A lose 2 electrons to form ions with a positive 2 charge. The atoms of the elements in group 3 lose 3 electrons to form ions with a positive charge. In this text, we do not use the group numbers of the transition elements to determine their ionic charges. In ionic compounds, the atoms of the nonmetals in group 7A, which is 17, gains 1 electron to form a -1. The atoms in group 6A, which is group 16, gains 2 electrons to form a -2. The atoms in group 5A, which is 15, typically gain 3 electrons to form a -3 charge. The nonmetal group 4A, 14, does not typically form ions, although the metals of tin and lead lose electrons to form positive ions. List the ionic chart. Table 6.2 lists the ionic charges for some common ions in the representative elements. Lithium positive 1, sodium, magnesium, aluminum positive 1, 2, and 3, potassium and calcium positive 1 and 2, rubidium and strontium positive 1 and 2, cesium and barium, cesium 1, barium 2. Nitride, N negative 3, oxide, O negative 2, fluoride, F negative 1, phosphide, P negative 3, sulfide, S negative 2, chloride negative 1, Br negative 1, I negative 1. They point towards the noble gas. They have the same configuration as noble gas.